For the second to last section that we will discuss from Chapter 20 will be Chapter 20.5 on nuclear fission. So let's take a look here at the worksheet on nuclear chemistry. So nuclear fission is a specific type of radioactive decay here where we have a heavy nucleus. So it has an atomic mass, right, of 200 mass number or greater, and it divides into smaller nuclei of, an intermediate size and usually one or more neutrons. So what happens here is in this specific reaction, we have an isotope of uranium, uranium-235, in which a neutron strikes the nucleus, it bombards the nucleus, and this means uranium nucleus in French, but this was the best image that I could find. So we have some outer nuclei over here. We have strontium-94, and we have xenon-139, and 3 neutrons. If we added up all these numbers, 94, 139, and 3, we would get our mass of 235 plus 1, we would get 236. And then as far as charge goes, we would end up with 92 if we just add 54 and 38, because the neutrons have no charge. So you see that this reaction makes sense that in the sense that uranium can create a strontium, a xenon, isotope, and then 3 neutrons. So we can use this information, this balanced reaction, nuclear equation, and find out the magnitude of energy released. So our delta E, our change in energy. So let's take a look here. We are given 3 different nuclear binding energies. Let's take a look at the calculation for this. And you won't be responsible on your exam to do this type of calculation, but since this is part of our curriculum for this semester, I figured we would do at least one example. We take the binding energies of the reactants and products, and we find the difference. So we have our reactant was the uranium. That's the 2.82 to the negative 10. This is our uranium, 235, and then this value here and this value here. These are our 2 products. We take products minus reactants. Remember, change in energy is always final minus initial, or in this case, products minus reactants to get a change or a delta value. So for 1 mole of uranium, right, we found our difference to be this 3.3 times 10 to the negative 11th joules per nucleus. We discussed earlier that this delta E value is the energy per nucleus, and when we multiply this by Avogadro's number, times 6.022 times 10 to the 23rd, 23 there, we find the amount of energy to be 2 times 10 to the 13th. Wow, so that's quite a bit of energy that is released from a mole, or Avogadro's number of nuclei. So that is everything for the section on nuclear fission. Next time we will have a brief conversation about nuclear fusion.